Hello, class. The next topic that we are going to discuss is something called resonance. And in order to understand resonance, we need to do a little history lesson and take a look at a molecule like this. So this is an alkene. So we have this alkene. And we could take that and expand it out and look at it kind of like this. And then I could even expand it out a little bit more. Recall from general chemistry. Now, I hope, class, when you hear me say that phrase, remember from general chemistry, and if you, in your mind, go like, yeah, I remember that, good. But if you're the student that says, I don't remember that at all, that is my cue to you. You need to figure it out and go back and remind yourself of it. Your mindset can't be like, yeah, that sounds somewhat familiar, but I really don't know what it means, and then leave it at that. You need to go back and remember it. So when we look at this alkene here, we have these two bonds right here, right? One of them is the sigma bond, and the other one is the pi bond. And when we look at that structure there, we could look at it kind of like this. So there's the pi electrons, and there's the sigma electrons, like that. And in this structure right here, these sigma electrons and these pi electrons, they stay in between the two carbons. They're localized. When the electrons are localized, that they don't move. They just stay in between the atoms that they're designated with. And so these pi electrons stay there. So sigma bonds are all, well, let me pause there, okay? So we have localized electrons. And the skeletal structure that I've drawn can represent the alkene very, very nicely. But there is a problem with the skeletal structures when the electrons are delocalized. When you have electrons that are delocalized, that means they move around. And so if electrons are moving, it's very difficult to draw what the structure looks like because the electrons are moving. See, these are localized. They stay there. Those 4 electrons stay between those 2 carbons, and there they are in this representation. But what if we had a molecule that looks like this, where we have a double bond, single bond, and a carbocation? And this structure right here has a name, and want to spell it right. Can you see that? Not very well, so let's draw it up here. It is called an allylic group. And an allylic is when you have at least three carbons, 1, 2, 3, and you have a carbocation, single bond, double. That is called an allylic, or an allyl group. You could call it also that's one way of saying it, that's allylic. You could say allyl, make sure you're spelling this right. That's an I, that's an O. So this right here is a allyl carbocation. That's probably the best way of saying it. So this is an allyl carbocation. Now this allyl carbocation is really, really hard to draw like this because these electrons right here can move around. They are delocalized. So if I redraw this, if we have a carbon here, double bonded to a carbon there, to a carbon, you have a hydrogen. You can't see that hydrogen there. Let's draw it like this. Hydrogen, cation there, hydrogen, and hydrogen right there, okay? That's what we're seeing here with the allele. Now, if I take this representation right here and draw this like this, so we'll say the lower one is the sigma bond, and the top one is the pi bond. What's interesting is these pi electrons. So we'll just write it over here. These pi electrons, they are delocalized. They can move. Those pi electrons right there, they can move over here. So when I take those delocalized pi electrons and move them over here, I get a structure that looks like this. So we have structure A and structure B. And the reason why we have two structures is because the pi electrons right here are delocalized. They're here, and then they're there. That's kind of the idea that I'm trying to portray here. So we have structures A and B, right? And so that's really hard to represent these two molecules when it could look like this and it could look like this. How do you just draw one structure? And so the skeletal structure, or the way to draw molecules using the skeletal structures, kind of falls apart here because it can't represent those electrons delocalizing or moving around. And so what we have here is a concept called resonance. So when we take a look at the allele, carbocation, what we have is this guy. And when you draw a double-headed arrow like this, that is called a resonance arrow. And that resonance arrow says, hey, there's A and there's B. All right? So we have two resonant structures. Now, listen to my words very carefully. This is a little confusing, but I want to explain, I'm going to explain it, and my hope is that it's not going to be that confusing, okay? So what we have is two resonance structures, but only one molecule. All right, one molecule. Now think about that for a second. How can you have two resonance structures, but only one molecule? Didn't Dr. Lawrence just say that we have molecule A and molecule B? I may have said that, but that's not correct. What we have is resonance structure A and resonance structure B. Okay? Now, to help with this, I want to share an analogy that I'm going to share, and then we'll bring it back to chemistry and make sense of this. Does anyone know what two animals need to breed to make a mule? So we want to breed a mule. What two animals do we need to bring together to make that happen? Well, we need a horse. And we need what? A donkey. If a horse and a donkey breed, they will make a mule. All right? Now let's make this a little bit more fun. What if we had a blue horse and a red donkey? So what would that make if those two mythical colored animals get together? We would get a purple mule. Sorry, I don't have a purple marker here. Okay, so blue horse, red donkey makes a purple mule. Now this is one mule, right? It's not one horse and one donkey. It is just a mule, one. And it is a purple mule. And so this purple mule, we call it a hybrid. It is a hybrid between a blue horse and a red donkey. So let me ask you this. Does this mule, does it all of a sudden one day say, I'm a horse? And then the next day it says, I'm a donkey? Or does it say, I'm a horse 1 second and a donkey another second? Does it go back and forth? No, it can't go back and forth because it is a mule. A mule is a hybrid between the two. There's only one mule. And so this is the same concept here with these two, what seems to be two molecules. They're actually a hybrid. So this hybrid right here, let's draw it above here. This hybrid and that you can't see that positive charge, so let me bring it down. There we go. That looks better. That's what the molecule looks like. When we try to draw it with skeletal structures, we could see it's this or that. But no, this molecule right here is not flipping between A and B, B and A, go back and forth, back and forth. No, it is just this. But we draw resonance structures to help us understand the reactivity of molecules. So very important things to understand. Molecule A, molecule B, they're not two separate molecules. They're just one molecule. They do not flip between each other. It looks like this. Now, how do I know what the resonance hybrid looks like? That's what this molecule in the middle is called. This molecule right here is called a resonance hybrid. When I take a look at the two resonance structures, how do I come up with this? And the way that you do that is you basically ignore the double bonds for the moment. Just find how many carbons there are. And so I'm going to come up with this. See, I'm ignoring the double bonds. I'm ignoring the positive charge. Okay? It's just boom, boom. So 3 carbons. Now, when I look at resonance structure A, I'm looking for the double bond. Where is it? It's on this side, on the left side. And so what I'm going to do to represent that double bond is I'm going to just show dotted lines. Because what it looks like is the double bond is present with the resonance structure A, but when you go to resonance structure B, it's no longer there. So you do the same analysis for this side. Oh, there's no electrons there, or pi electrons, be more specific. But then when I go to resonance structure B, oh, there's pi electrons. So I got to represent those as dots right there. And then I can go to the charges. I can see, hey, there is a positive charge there. But then when I look at resonance structure B, there's no positive charge there. So you can't just go positive charge, because now look at that molecule. That's a +2. That's not what we have. We only have a +1. So that's not how we do it. What we have to do now is introduce that delta symbol that looks like this. That's delta. And you go delta plus. So this carbon has a delta plus. And that delta is telling us that we have a partial positive charge because it's there and not there. So it's partially there. And we can do the same thing. Neutral, positive. So it is a partially positive carbon. And so that's how we would draw this resonance hybrid. But this up here looks different than this down here in orange, right? It does, okay. So this is how I want you to draw resonance hybrids. You're going to show me where the partial positives are, where double bonds. So when I look at this, I could say this double bond is breaking and forming. This double bond right here is breaking and forming. That's what the two resonance structures are showing me. So this resonance structure, or this resonance hybrid right here in brackets, is telling me, hey, bonds breaking and forming, and we have an overall charge of +1. This representation down here, also a resonance hybrid, is showing us where the partial positives are. And I know those partial positives because I'm looking at the resonance structures. So if you just numbered the carbons, 1, 2, 3, you can see that we have a partial positive on carbon 3, boom, and we have a partial positive on carbon 1. All right. Another key point to understand, it is only the pi electrons that are delocalized. The sigma electrons don't move. So what are we representing with this solid line in the hybrid? That solid line are the sigma electrons. Sigma electrons are the solid line. And then the dotted lines are the pi electrons. The dotted lines. So another thing we can say is the sigma electrons, solid line, are also localized. They're localized electrons because they don't move. But the pi electrons do move, as you can see, the pi bond there, then there. So the pi are delocalized. Very important to understand. Now, when you have resonance for a molecule, it is a very, very stabilizing effect. So if you had a molecule that looked like this, oh, let's clean this up here. We have a double bond there, okay. When we compare this molecule here, it is more stable than a molecule that looks like this. This molecule right here has no pi electrons. There's no resonance hybrid for this molecule because there are no pi electrons that can delocalize. So whenever you have the compare and contrast between a molecule that has a positive charge, but the electrons can move around, or the pi electrons are delocalized, it stabilizes this molecule, whereas this molecule is not stabilized because there's no resonance. So if we drew an energy diagram right here, we would find the allyl molecule lower in energy versus the primary cation is going to be higher in energy. And so this stabilization right here is called resonance stabilization. Another way of looking at it, if you can take electrons and delocalize them and make them move around, they're more happy. And when you're more happy, you're at a lower energy state and more relaxed. But when electrons are constrained or localized and can't move around, they're higher in energy, they're less comfortable, and they just feel restricted. And electrons want the freedom to move. Very, very important. Now, in organic chemistry, arrows mean different things. And they're very, very important. You cannot mix up the arrows. So let's look at the allyl again. All right. Now, remember what this arrow is called? The double-headed arrow? That's called a resonance arrow. Now we have another set of arrows called curved arrows. Curved arrows show you the movement of electrons. Now, that is a very, very simple sentence and a very simple statement. It only shows you the movement of electrons. It does not show you where atoms go. It just shows you where the electrons go. So in resonance structures, when you are using curved arrows, atoms do not move. And a curved arrow looks like that. You have the head of the arrow, where there's the point, and then you have the tail. And a curved arrow is used to show where the electrons start Electrons start at the tail, and then where did those electrons move to is at the head. So for example, I can draw a curved arrow telling you and me where these pi electrons are moving. So I can see that these pi electrons are moving over here. So what I do is take the tail of the arrow and draw it in the middle of these two carbons. You take it and say these two electrons, the pi electrons, are going to come and move over there. So what do we have here? We could look at it this way. Those two electrons are moving over here. Like that. So let's draw it below in the way that I want you to know how to do it. So we have resonance arrows. So we have these pi electrons right here, and we're going to take them from the center and draw the arrow to the center between these two. And so that orange arrow is saying these pi electrons are going over here. Now, we could draw a curved arrow for this guy. We could say, hey, these electrons right here, draw the center to the center, like so. And we go back over here. So this orange arrow right here says these pi electrons right there are going to move over here, which they did. Then you have that. Now, when you draw when you draw curved arrows, there's another arrow like this. It's a curved arrow, but with only one hook. Do you see my curved arrows that I'm drawing have two hooks? So we're going to learn about another mechanism or another arrow like this later. But you have to be aware that you have to draw the double arrow when you're drawing curved arrows. Okay. So you already see the answer here, but what I want you to be able to do is if I gave you this molecule right here, and I draw the resonance arrows for you, like this, I want you to draw the resonance structure over here. So what you do is when you look at that, you're like, hey, atoms don't move. So I just draw the atoms. There's a carbon, carbon, carbon. Boom, boom. That's all I do. How many hydrogens are here? There's a hydrogen there, a hydrogen there, a hydrogen there, hydrogen there, and a hydrogen there. Do any of the hydrogens move? No, no atoms move. So they're all there. Do not move atoms. Okay? So what is this orange arrow telling me? It's saying the pi electrons between here move here. So all I have to do is move those electrons over there. But now I have to look at the charges. So this atom over here is neutral because it has 4 bonds. This carbon is neutral because it has 4 bonds. And this carbon over here is positive 1 because it has 3 bonds. So now I come over here and reevaluate. I look at this carbon here. 4 bonds, neutral. 4 bonds, neutral. Carbon with 3 bonds. So that has to be the positive charge. So every time you go from one resonance structure to another, draw in all the atoms exactly where they are. Don't move them. Don't rearrange them. Just move the electrons to where the arrow is showing you to put them. And then take a step back. Say, okay, now I have to calculate formal charges and just recalculate. Okay. So there, with drawing resonance arrows and curved arrows, there are some major rules that I'm now going to go through with you because resonance is another really important thing to make sure we understand. And I already talked about that in the last video of how important it is, okay? So we're going to go through some rules. Now, when you're looking at molecules and wondering if there's resonance structures, you can't memorize all the molecules. There's just almost an infinite amount of molecules. So you can't memorize resonance structures, but you can definitely learn principles. And so there's some principles that I want to share with you. And another way of looking at it is patterns. Looking at some patterns for resonance structures. And the first one that we saw was the allylic one. And this is going to have a resonance structure like what we've seen already, right? So what pattern do we see here? Is whenever you see a positive charge adjacent to a double bond, then you are going to have resonance structures. And we worked that one to death already. But then you can have, what if you have something that looks like this? Negative charge. Right? What if you have something like that? Can you draw a resonance structure? And this one is when you have a lone pair adjacent to a double bond. So I want you to write that down for this one. If you have a carbocation adjacent to a double bond, resonance. When you have a negative charge with a lone pair adjacent to a double bond, you have resonance. Let's grab a different color here. So what can happen is that the lone pair right here can resonate down to form a double bond there. And then these electrons, these pi electrons here, have to go to the carbon. And so the resonance structure now is going to look like this. Boom, and then the lone pair there. Now, why do you have to okay, what's going on here? You have to just look and notice that the atoms have not changed. So if I draw this structure out, I would have a carbon double bonded to a carbon to a carbon. And then this carbon would have a hydrogen and a hydrogen. Hydrogen. How many hydrogens does this carbon have? Well, it has a negative charge, right? So if it's a -1 charge, then that means that there are only 2 hydrogens there and the lone pair there. That makes that negatively charged. Right? And so what we're doing here is I notice that we have a negative charge or lone pair adjacent to a double bond. So those electrons right there can come and go in the middle. And if, this is really good skill to have. If, do you see up here I drew 2 orange arrows? What if I only drew 1? What would happen? Well, you just keep all the atoms where they're at. Because, like I said, resonance structures, you do not move atoms. Okay. I am just following what the orange arrow says to do. It says take the lone pair, move it there. That's what I did. But is that correct? Well, remember, you have to calculate the formal charges at the end of it. So when I go and I look at this, let's see if we can do it blue. What's the formal charge on this carbon? This carbon has 4 bonds, so that's a formal charge of 0. If I look at the one on the very right, the formal charge is 4 bonds, so that's 0. But then when I look at this one right here, a red flag should be going off in your head. This carbon has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It has violated the octet rule. That is a carbon with 5 bonds. That does not happen. So I know I made a mistake because carbons cannot have 5 bonds. So I need to reevaluate. But the pattern that you're supposed to see here is that you use 2 arrows. So this comes in, these pi electrons have to move to the carbon. Do you see how I'm starting from the center of that pi bond? And I'm saying the electrons go on the carbon. And so that's what I have to draw. So I'm going to take that away. and say, hey, the lone pair goes there. Now I recalculate the formal charges. So that carbon has 4 bonds, that's neutral. That carbon, 4 bonds, neutral. That carbon, 3 bonds and a lone pair. That makes that a -1. Okay. Let's look at another pattern here. And the next pattern is when you have lone pairs adjacent to a positive charge. So if we had something that looked like this. And we had some lone pairs and a positive charge there. When you have that situation, you can take one of the lone pairs. It doesn't matter which one you take. You could take either one. You're just going to start and draw it there. Do you see how I'm putting it right in the center between the carbon and the oxygen? I am now forming what? I have to draw my resonance arrow, and I draw all the carbons and atoms just how they are over here. I don't change anything. It says I'm going to, this lone pair right here wasn't used, so it's still there. But this lone pair was moved between the carbon and the oxygen. So I represent that with a double bond. Now I evaluate, where's the formal charge now? Well, you got to get really good at looking at skeletal structures and knowing exactly how many atoms there are. That has a hydrogen there, right? So that hydrogen is still there. So nothing changed with this carbon. That's the same. Nothing changed with these two. And nothing changed with those two. So I don't need to recalculate those. But look, the oxygen now has a double and a single bond, whereas it only had a double, or 2 bonds right here. And it had 2 lone pairs and only 1 lone pair. So we have to recalculate the formal charges on this guy, this carbon, and this oxygen, because when you look at the 2 resonance structures, the electron count is different. So let's look at the carbon here. So how do you calculate the formal charge? Well, that carbon has 4 valence electrons. And I just count bonds this carbon's bonded to. Or I count how many bonds this carbon has. It has 1, 2, 3, 4. 4 minus 4 is 0. So that carbon there is neutral. Now I look at my oxygen. If I look at my periodic table, it says, hey, that's in group 16. So that's 6 valence electrons minus 1, 2, 3, 4, 5. So that's a +1. So that oxygen now is a +1. Now, one really important thing to remember, and a good way to check if you've done it correctly, is the overall charge of this resonance structure and the overall charge of this resonance structure has to match. If you have a +1 charge on this side, you have to have a plus charge on this side as well. You have to. If any of that is different, if this is +1 and this is neutral, you know you made a mistake somewhere, because those overall charges have to match. Another, under the same pattern, what if you have, let's say, a structure that looks like this? A plus charge, 3 lone pairs, and a plus. Wait. That's not right. A single bonded oxygen with 3 lone pairs is a negative. Now, remember the pattern I said? if you have a lone pair next to adjacent to a carbon, you can have resonance. So we could take one of these lone pairs. It does not matter which one. You could pick this guy, or that guy. And you just draw out the arrow coming down like that. Now, I'm just drawing all the atoms where they're at. I used these lone pairs, so I have these two left over. And I said I took that lone pair and put it right between. Now I reevaluate. What's the formal charge? Well, what changed? Something changed with this oxygen, something changed with that carbon. So we will see that the formal charge on this oxygen is neutral, and the formal charge on that carbon is also neutral. Now you may be like, whoa, 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 Dr. Lawrence said you have to have the same charges on both sides, or for both resonance structures. No, I didn't say that. I said the overall charge of the molecule has to be the same. So when we take a look at this blue molecule, we see we have a positive charge and a negative charge. So this molecule is neutral. We come over here. This whole molecule is neutral. So that works. That is okay. Now you can also look at the opposite here. What if you have a ketone like this, and we have lone pairs there? You can, when you have an oxygen atom like this, let's see here. Okay, the rule is when you have a pi bond, which basically means a double bond, when you have a pi bond between two atoms, so we have an oxygen atom here and a carbon atom here. When you have an what's the word am I trying to find here? When the two atoms have different electronegativities, you can have resonance. So when we look at the electronegativity tables, we can see that oxygen is more electronegative than carbon. So when we have that, we could take the pi electrons, two electrons in that double bond, and move it to the more electronegative atom. And so we still have the single bond, but we broke the double pi bond there. These lone pairs were already there, but I'm taking two electrons in that pi bond and moving it there. Now I have to reevaluate the formal charge, and we will find that the oxygen is going to be -1, and this carbon right here is going to be +1. So the trick is when you look at a pi bond and you have two different atoms, if one is more electronegative than the other, you can have a resonance structure. All right. Let me show you some tips of what not to do with resonance structures. The first one is this. Okay. Never ever draw the tail of the arrow starting with the positive charge. Now, why is this so bad? Because the tail of the arrow is saying that we have electrons that we are moving onto the oxygen atom. That's what the arrow is showing, okay? But how can you do that when you have a positive charged carbon? When you draw out that carbon, what do you have? You have a carbon, and then you have two hydrogens. So now when we look at it, where's the electrons? There's no lone pair. So you're not bringing any electrons. So you can't do that. right? So never, when you look at something that we've seen already, this is not a resonance structure. That is 100% wrong because you're not showing where the electrons are coming from and going. You're just showing me where the positive charge went. That's not resonance. Resonance is showing us where the electrons are going, okay? So the correct way to do this top example, whoops, back that. Let's draw it over here. A more accurate resonance structure here would be the lone pair here coming down, like so. And then we draw a resonance arrow. We did not use that lone pair, so that stays there. We said that lone pair, now it's going to form a double bond there. Okay, so we evaluate formal charges. The carbon now is neutral. The oxygen now is going to have to be positive. So that right here, okay, this little piece right here, that's the correct way to do the resonance structure from up here. Okay. The next thing that you should never ever do is when you have, let's say we have this guy right here. Never ever draw your resonance arrows where you take the electrons in the pi bond and just throw it off into space. The electrons aren't going to just go off into space. You have to show exactly where those electrons are going. So the correct way to draw this resonance structure would be you take the electrons and say, hey, they're going right there on that oxygen atom. And now we reevaluate the formal charges, like so. There's some other really important things to know. And one textbook refers to these two rules that I'm going to share with you as the two great commandments that thou shalt never, ever break. And the first great commandment, according to the Klein textbook, is thou shalt never, ever break a single bond, like this. So what would that do? That is, most students would be like, hey, that would look like this. That is clearly not a resonance structure, for one, because it breaks the great commandment, never break a single bond. Two, you have moved atoms around now. Look at that. You have 3 carbons here, 2 carbons there. You've moved them. You don't move atoms. They stay in place. So that is a no, no, no. And then the second great commandment is thou shalt not break the octet rule. And this is the one that gets a lot of people in trouble. So what if I had something like this? Okay. Is this valid? Can I do this? Let's take this lone pair here. What if I took it and put it like that? You see that's a double-headed arrow. Now, let's be consistent here. My double-headed arrows are not filled in. They've been just like that. So let's stay consistent. What would that structure look like? It would be a double bond CH3. Double. Is that valid? No, because let's expand this out. Do you see the problem? Do you see it? Look at this oxygen atom. Does it break the octet rule? There's 2, 4, 6, 8. No, it doesn't break the octet rule. That's fine. What about this carbon? 2, 4, 6, 8, 10. Boom, just done. That's wrong. You cannot do that. Cannot break the octet rule. No, no, no. Okay? So let me show you one more example. I know we're short on time here about do not break the octet rule. And this is what I'll leave you with for today. Okay, let's see here. Let's say we have a positive charge there and a double bond there. Okay? Now, I'm not giving you the answer. I want you to think about this and come to class and tell me what you think. And we will call this problem 1 and problem 2. And what you're going to do is, for problem 1, is that an okay resonance structure or curved arrow? Can I do that? And I want you to draw what the product is. And then I want you to do the exact same thing for this. Is that valid? And what would the structure be over here? So that's what we're going to talk about when we come to class. Okay? If you have any questions, concerns, please reach out. I'm more than happy to help, guys. I'm working with you to help you learn this material, okay?